Okay, welcome back everyone. We're going to start a session on interop with 4 different talks. The first 2 talks will be related to intent, and we have Andrea Canidio from CalSwap, who will be the first speaker. Round of applause, please.
Thank you, Justin. Hello. Clicker. All right, so just as for introduction, one of the characteristics of blockchain is that it is permissionless and adversarial. Now, permissionless means that anybody can show up and create new things, including new type of financial markets with different mechanism, fees, way to concentrate liquidity, whatever. And this is all cool because it's all innovation. However, it also leads to liquidity fragmentation, which is obviously a problem from the point of the user. And it's adversarial, like it's the dark forest. So for example, if I'm trying, sandwich attacks and other type of attacks. The 2 things together implies that exchanging assets efficiently and safely on the blockchain can be challenging for the user, okay? For the perhaps not super sophisticated user. And if you're wondering what's the picture, I asked GDP to draw a fragmented sandwich. So that's what came out. Okay. All right. So what is the solution? So one of the main solutions for this problem are trade intent auctions. So what is a trade intent? So a trade intent is an order to swap 2 assets in which the person submitting the order will specify, obviously, a sell token and a sell amount and a buy amount and maybe a limit price. But importantly, will not specify an execution path. So it will not say, oh, buy this on this AMM or on that AMM. We'll leave that blank if you want. And then there is a mechanism, an auction, that will then complete this order by specifying the execution path. And the way it's going to work is that there's going to be some specialized entity called solvers that are going to bid for the right to execute the trade. And let's just say for the moment that the solver providing the best price wins. Obviously, best price is in quote because the exact mechanism matters a lot, and the rest of my talk will be precisely about that. And also importantly, in most of this mechanism, once the solver announces a price and wins, it has committed to this price and bears all the risk in case, for example, he gets sandwiched afterward, okay? And trade intent auction became very popular. This is a Dune query that calculates the volume going through the 3 main protocols handling trade intents from January 2023 to last month. And you can see a nice growth. And last month was a record month with 9.5 billion USD intermediated via this mechanism on mainnet alone. Okay? And currently, there are 3 main protocols and 2 main mechanisms. Okay? The 3 protocols are Cow Protocol, where I work. And the main mechanism there is a batch auction. Okay? I'll discuss in a second what it is. Whereas the 2 other important protocols here will be 1inch Fusion and Uniswap X, both of whom employ a different mechanism, different type of auction, a Dutch auction. Now, what are those 2 mechanisms? Well, a batch auction is an auction in which the auctioneer receives multiple intents, so multiple orders, and is going to auction them off all simultaneously, like with a group of those orders. And each solver proposes a price for each of the trade in the batch, or at least the one that this solver can execute. And then, the best solution wins, where best here means like a total value return to the users. And okay, as you can imagine, sometimes you may need some sort of outside price to determine what is the best solution, because one proposed solution may give more to a user, a bit less to another user, and another one the other way around. So you have to have a notion of how valuable are those assets to make a final scoring of the proposed solution, okay? Now, a Dutch auction, again, Dutch auction, there are a lot of details, but what is going to be important for my presentation is that Dutch auction are instead separate auction per each trade intent. So trade intent comes in, 1 auction. Another trade intent comes in, 1 auction. If 2 trade intents come in simultaneously, well, 2 separate auctions. And okay, the Dutch auction is the descending price auction. and it is strategically equivalent to a first price auction. So you can think of it as a first price auction, meaning that from the point of view of the person that is bidding, you just have to think what's the maximum I'm willing to bid, and that's it. So, and it would be the same if this was a first price auction. Now, each of these mechanisms has some advantages and disadvantages. And again, I'm not going to talk too much about the Dutch auction itself, but rather a situation where we have individual trade auctions. So first of all, this is a world where there are often complementarities between the different trades. So it could be that you have two traders that want to trade the same assets, but on opposite direction. This is the kind of simplest example. In which case, you know, a solver, if you have a batch auction, a solver could just say, hey, look, you know, here are the great prices that you can get if you just trade with each other. You could have situations where all the trades on the batch, you want to execute them through several steps through intermediate assets, and maybe this coincidence of wants arise in intermediate steps of these multi-hop trades. You could have gas savings. So anyway, there are many reasons why you can squeeze out additional efficiencies by putting multiple trades together, and batch auctions are designed precisely to allow solvers to figure out where those efficiencies are and exploit them and get good prices to the user. So in a sense, batch auctions are really good at that. On the other hand, you can think that solvers are somewhat specialized. So there are solvers that are great at certain type of trades and solvers that are great at some other type of trades. Here, a batch auction will kind of force one solver to win all the trades, whereas perhaps you will prefer to split the trade in the batch, some to one solver and some to another solver. So this will be a case where the kind of Dutch auction or individual trade auction will be better. Batch auction is better at generating competition between solvers. Why is that? Think of a situation precisely where solvers are somewhat specialized. If you have one batch auction, you force all solvers to compete among themselves. So the full set of solvers compete with the full set of solvers. Whereas if you have individual trade auction and you have, say, 3 solvers that are competitive on that type of auction, well, essentially only those 3 solvers will be competing in one auction, 3 solvers will be competing in another auction. So batch auction is better at generating competition between solvers. However, batch auction can be unfair in the following sense. If you take the mechanism just literally, the winner is simply scored by the total value returned to the users without much regards to how this value is shared. So it could be that the winning solver, in fact, gives a great deal to one guy and a shitty deal to another guy, and you know, maybe this second guy would have been better off in a Dutch auction or another mechanism. Right? Now, currently, at least in the way Dutch auction is implemented at KAO protocol, there is a thing called EBBO, which is Ethereum Best Bid Offer, like an adaptation of the NBBO in traditional financial market. And essentially, you can think of it as a routing algorithm that we run after the auction finishes to check whether everybody in the all traders got at least what our routing algorithm would have gotten them. Okay, so it's an ex post check. And when we find a violation, we ask the solver to reimburse the user. But this is problematic. First of all, it's our routing algorithm, and you know, we are not solvers. So solvers have better information. So ideally, we would like to use the information of the solver to determine this kind of benchmark. On top of that is a centralizing vector. Ideally, we would like to be decentralized, and it's a gigantic overhead. Okay. Note also just one side note that the batch auction as implemented at KAOSwap also has another element, which are subsidies to the solvers. So we pay solvers, the winning solver, the difference between the value they generate and the second highest bid. This is to generate truth telling on the side of the solver. So they just can report the maximum value that they can generate without worrying about shading bids. Okay. But this won't be part of discussion today because it's something that we do and I think makes a lot of sense to do, but you could do it in a for example, straightforward trade by trade first price auction. I mean, it's not specific to a batch auction. It's just something additional that KAO protocol does. All right, so what is the research question then? You see, we have these two mechanisms. They each have advantages and some disadvantages. And we could argue, okay, this is becoming an important market, okay? It's important quantitatively, and in a sense, in the context of blockchain, blockchain, you can do many things with blockchain, but primarily in terms of volume and usage, it's DeFi, okay? And swapping is somewhat the most basic act you can do in DeFi. If you cannot swap, then all the rest of the stack kind of cannot work. And so this is also important to make this very basic act as efficient as possible, okay? So you may want to know whether we can find another mechanism that can result in batching or specialization, depending on whether the benefit from trade, like having these trades executed together, is higher or lower than the benefit of solver specialization. Sorry. It does generate competition between solvers, and it is fair. Where fair is really the sticky point, because if I didn't have fair, I could have opened an auction theory textbook and look at, plain combinatorial auction, and I would have gotten my answer. I mean, okay, after digging a bit. But fair is where this problem becomes difficult, because in the definition of fairness I kind of already introduced in the previous slide, essentially I am comparing the outcome when trades are batched to an outcome of a sort of an alternative auction that I could have run, where instead each trade was auctioned off individually. So I am really comparing the outcome of a mechanism with the outcome of an alternative mechanism that I could have run, but I didn't run. Okay, so I don't really know what would be the outcome there, all right? And so in the literature, there are many definitions of fairness when it comes to allocation mechanism, like auctions, so on and so forth, like envy freeness and so on. But they typically tend to look at within a mechanism, Mike got this, is Mike envious of what Tim got? So same mechanism, different people. Whereas here is really just as kind of a different concept. So within a mechanism, comparison with another mechanism. And the problem is precisely that the auctioneer doesn't know what would have been the outcome had I run a different auction, okay? Also, the problem is framed in the context of trade intent, but there was a presentation a year ago here by someone from Espresso System that was kind of in a more intuitive level talking about the sharing of efficiency when you have what was it, like a share data availability layer, a share sequencer, there was a discussion. And a kind of intuitive level was making the point that, okay, I would have loved to know what would have happened had I run a different mechanism, but I don't know. And so in some sense, it was similar here. And Ari Jewell yesterday was talking about Prof, how you can do the background of an entire bundle of many transactions. And I guess also there the question becomes, oh, well, if you want to have a fair redistribution of these payments, you will have to calculate or have notion of what would have each this transaction gotten had I auctioned it off individually, okay? So in other sense, the research paper and the presentation is very geared to this one case, but I think if you zoom out, the research question in fact becomes relevant also in other contexts. Okay, so as I said, my presentation is based on a research paper in this which I co-authored with Felix Haneke, a colleague at Chaos Protocol. In this research paper, we write down a theoretical model of trade intent auctions with all the mathematical kind of detail required, where what distinguishes that model from a standard combinatorial auction is a feasibility constraint that determines how much each solver can return as a function of how many trades it wins in the auction. Then now we have this theoretical framework. We can use it to study the two most commonly used mechanisms, batch auction versus separate individual auction, and we have some results there that are kind of in line with what I was discussing earlier. And then we use the model to propose a new auction format that we call the fair combinatorial auction. The idea is precisely to formalize a notion of fairness of a mechanism when compared to another mechanism. Now, to make it simpler here, let's just say that this fair combinatorial auction turns out to be a merge between a batch auction and having individual trade-by-trade auction, where I only allow the batch to form depending on the outcome of this individual trade-by-trade auction. Of course, I'll explain more in detail later. And where the paper spends many pages is to show that, okay, this is a bit like cooking. Like, this is one auction on top of another auction. Whether you get something that makes sense or not depends on the details of these auctions. So there are cases where after going through this auction on top of an auction, what you get out is something that has the same equilibrium as a batch auction, so it really does not do anything in terms of fairness, and other cases where it does, okay? So the detail matter a lot. But for today's presentations, I am gonna skip all of it and just tell you what is this fair combinatorial auction for the case where it does generate fairness guarantee. I'm going to kind of skip the cases where it doesn't. And also because in some sense, these are, I'm maybe taking off my more academic hat and putting on my more like product hat, because this is the one that we are planning to then implement sometimes next year at Cow Protocol to replace the batch auction. So in some sense, I'm zooming in into the thing that will be more relevant, practically speaking, for building the protocol. OK. Long introduction. I don't see the time, so someone has to. 10 minutes. OK. Very well. I actually have extra slides with the model and the math. I don't know, maybe I'm going to bring it up if time allows, but these are just at the end. So what is this fair combinatorial auction? So fair combinatorial auction is it's a combinatorial auction. So a combinatorial auction is an auction where the auctioneer auctions off multiple objects and allows bids that are conditional on the on which object a bidder might receive. So essentially, here a solver can say, hey, if I win this trade, I'm going to return 10. If I win this other trade, I'm going to return 1,000. But if I win both trades, I'm going to return, I don't know, 11 and 1,010. You know? So it's actually specifying how much he's going to return as a function of the set of trades that he's going to win. So each solver here can make multiple bids, where some may be on individual trades, and some may be on groups of trades, let's call it on a batch. OK, this will be just a standard combinatorial auction. The fairness part comes from this filtering step that it applies only to batch bids and works in the following way. First, you only look at the individual trade bids. Okay, leave aside all the batch bid and just look on bids on single trades. And then you can calculate the outcome of several simultaneous first price auction with those bids. Okay? And this is your reference outcome for fairness. So you can say, OK, if I leave aside the batch bid, this is as if I am running an auction per trade, and I have received a bunch of bids in this auction. And now, depending on the auction format, I can calculate what would have been the outcome on those individual trade auctions. Let's say it's a first price auction, so essentially I'm just going to looking at the best bid on each of these possible trades, right? Because I'm only considering bids on individual trades. So I'm just looking at those and thinking that I'm running auctions all on one auction per trade. And then essentially I say, OK, this is an outcome I will get if I was to forget about the batch bids and only essentially allocate those trades to the best bidder on each individual trade auction. And then I use this reference outcome to filter out a batch bid if it is worse than the reference outcome for at least one trader. So this is my reference for fairness, and I say, OK, look, therefore, I'm moving forward with a batch bid only if everybody who ends up being batch is better off relative to this counterfactual outcome. OK? And then I have a bunch of surviving bids, the individual trade bids, and a bunch of surviving batch bids. And then I recompose them as a way to maximize an objective function. OK, if you want to do the full value maximization, then maybe NP-hard. You can choose to do something different. That's not particularly important here. But you just elect winners on this remaining set of bids. OK? Now, OK, this was fast, so let me repeat. More like if you're a visual person, I'm going to illustrate it again. By the way, as you can notice, I'm not only previewing for you the new mechanism at CowSwap, I'm also previewing for you the new visual identity at CowSwap, because we really believe that the next driving narrative in crypto that will onboard the next billion user is the Eli 5 narrative, explaining like I'm 5. So that's kind of, we are starting working on this direction. Okay, jokes aside, I'm sorry. Like, I wasn't expecting my slide to be so big, so I feel a bit ashamed of this screen. In any case, so I have my order books that contains all the orders that I've received. I have two friendly solvers that are bidding in this auction. Okay, as I said, it's combinatorial. So these solvers can, on one hand, bid on individual order. So say, okay, solver one says, look, on the green order, if I only win this one, I'm going to return a certain amount, which is not written there, okay? And similar, solver two can say, oh, you know, if I only win the green order, this is what I can return. Similarly, for a bunch of other orders, some orders only have one bid, some orders have no bid. At the same time, they can also submit batch bids. Let's say, as an example, that they only submit one batch bid per solver here. And again, it contains each batch bid contains some of the orders in the order book, but they can, for example, a green bid, so the bid on the grid order here does not have to be identical to the bid on the grid order here. So for example, this I draw it bigger because perhaps solver one can return more tokens to order green whenever this order green is part of a batch versus by itself. Okay, this is kind of the idea. Now I have my bids, some of individual orders, some are batched. Then I compute my counterfactual reference outcome for fairness. As I said in my example, this is a first price auction. And so essentially I'm just taking the maximum of the bids submitted per each order. Okay, this is how I construct my reference outcome. And then the next step is the filtering. And this is essentially, I'm kicking out those batch bids if either of the order for which I have a reference outcome, the batch bid is in fact worse than the reference outcome. And then as an example, let's say that the first batch bid survives the filtering, where the second batch bid does not survive, so it's filtered out. And in this case, the winner will be this combination of bids, okay, where I have the batch bid by solver one plus the individual order bid on the purple order by solver two. Okay, that's the way it works. Yes. Okay. Now let me just going back for 1 second. Now here I have put first price with a star and whatever, because it turns out that, for example, if you build the same mechanism with a second price auction, so where this reference mechanism is built, it turns out this auction becomes in equilibrium identical to a batch auction, so you have no advantages relative to just doing a straight batch auction, meaning this fair combinatorial auction does not generate any fairness guarantee in equilibrium. But if you do a first price auction, it turns out that it does, as I explain in a second. Also, just to fix your ideas, obviously this part here looks like an individual trade, so looks like 4 different separate auction on different trades, okay? And if I only had this part, solvers will bid in a certain way. This looks like a batch auction, and if I only had this part, solvers will bid in a certain way. Now, what you should not assume is that when I put everything together, solvers are continue bidding as if it was, on the one hand, an individual trade bid, and on the other hand, a batch auction. So the whole point of the analysis is that, well, if you put together, this creates additional strategic considerations, and solvers might actually change the way they bid relative to a straightforward batch auction or a straightforward like Dutch auction, for example. In particular, the novel strategic considerations you have to consider are, in some sense, 2. The first one is that now, as a solver, I anticipate that my bid on individual order will end up affecting this reference for fairness and might, in fact, end up kicking out my opponent batch bid as unfair. This will mean that, relative to just a standard first price auction, I'm tempted to bid higher as to try to kick out my opponent. But the mirror image of this is that, okay, if I think I'll be successful at kicking out my opponent from the batch bid competition, I might actually lower my batch bid because I expect less competition there. So the 2 effects you have to keep track of is that, okay, now I want to bid higher in these individual bids, I may be lower in the batch bids. And as a result, what we show in the paper, that in equilibrium, the mechanism generates fairness guarantees because each solver always returns strictly more to the trader than if you had a simultaneous first price auction. So in some sense, this is strictly better for the traders than having separate Dutch auction. You can get in equilibrium either batching or specialization, depending on which, whether is there higher benefit from complementarities or there are strong benefit from specialization. But if the equilibrium is batching, as a total value, a return to the user might be lower in equilibrium than if you had done a straightforward batch auction, okay? Which means that, to summarize, this mechanism generates fairness guarantees, so everybody gets more than in this first price auction benchmark, but sometimes at the expense of total value return to users, okay? I think, okay, so I just conclude. Yeah, trade intent auction are an important piece of DeFi. As I said, that's very central to a lot of what we do, and they're also central now in this debate about chain abstraction with extension of this mechanism to cross-chain swaps. There are efficiencies from batching, so it would be a pity not to exploit them. At the same time, how to share them, it's not straightforward, so there are problems with the fairness. And here is a mechanism that, in fact, kind of addresses this problem, and we show that it actually works in generating fairness consideration and exploiting efficiency from batching. All right, thank you.
Thank you. Thank you, Andrea. Any questions? Please come forward.
Hi, thank you so much. On the practical note, I was wondering if your results hold, or how do you realize those results in practice? Speaking with a product person who is also implementing those theoretical results in practice, what is the difference between the stylized model that you have provided versus a product that is then working on chain? And how does this intermediate step with having two auctions or a solver in between the information that you're aggregating from users help to realize this mechanism?
I mean, I can tell you how we plan to implement it. Then, of course, maybe in a different setup will be different. But first of all, there are no separate steps. It's just one algorithm that collects bids on individual trades and bids on batch bids, and then runs an algorithm to do the filtering and then reaggregation to a set of winners. So it's really just something that you can run. I mean, you can think of if you have an auctioneer can be a smart contract, or auctioneer maybe is some, in the case of Cow Protocol for the moment, is an off-chain component. It's just code inside the auction, the software that runs the auction that will do that. From the point of view of Cow Protocol, yeah, I mean, another thing that we want to guarantee in our auction is uniform clearing prices, that there can be only one price per token per block. And this is going to be done by essentially, here I have discussed it as if, the bids are on the individual trades, where in fact, there's going to be an intermediate step here where we aggregate trades on the same token pair and the same direction. And this is the smallest unit on which solvers can bid. So you can generate uniform clearing prices also in this mechanism. Yeah, I mean, obviously, there are a lot of infrastructure things to do because now you have multiple bids and you can have multiple winners. Another important thing, as I said earlier, is how you specify rewards for solver in this mechanism, which is a bit of an open resource question on our end. Yeah, I mean, I don't know how this is interesting for the audience, but there are a lot of additional interesting details that you need to think about if you want to bring this to the product. But that's what I think you can do it. I mean, you have to go through a list of things that you need to figure out, and yeah.
Yeah, hey, thanks for the talk. I was just wondering whether the fairness results also holds if you have bidders colluding with solvers, or if it sort of assumes that the solvers are, like, what if a solver also runs a bidder? Can they then
If the solver runs, so can submit orders to the
Yes.
auction?
Yeah. Like oftentimes fairness or these types of results are a lot harder once you have collusion, right?
Yeah, I did not think about collusion. And yeah, they are much harder when you think about collusion. But here, fairness is very much from the point of view of the user. So the question is whether you think you can make things worse for the user by submitting an additional, as a solver, submitting an additional order. I don't know. I don't think, yeah, we can continue the discussion later. So it's a bit of a different notion of fairness relative to what is already existing in the literature.
Yeah, I mean, it's stronger, no? Like, it's just an additional scenario.
Yes.
Okay.
I don't know.
Okay, thanks again.
Okay,
Andrea.
thank you.
Next up, we have Omar Zaki from Composable Finance, who will be talking about intents again and giving a review of the current intents landscape. A round of applause, please.
Hey guys, can you hear me? Good? Okay. Yeah, so intents, everyone's talking about intents these days. We're very interested in intents because we fundamentally believe that the way we're going to actually unlock the next sort of like 100 million billions of users of crypto is if you literally can be able to take out your phone and basically speak to it and see what happens. And so we're sort of scraping the surface of intents with, having swaps and things like that. But now with AI agents and other things like that, popping up, I wanted to sort of do a presentation about where we actually are with respect to intents, what actual systems do we have out there that execute intents, and how can we sort of enable this next step of sort of the Valhalla moment when you plug AI agents on top of intelligent intents, essentially. So yeah, as many other speakers have talked about, intent benefits, there's many, user experience, but also best execution. Having a competitive network of solvers competing to fill user orders also results in less MEV as opposed to just doing a swap directly on chain. Where I see solvers eventually evolving to is being able to do a lot more complex computation where they're able to sort of process if this then that statements. The issue that we've seen in the market is obviously solvers are really good at one thing, which is swaps and trades. And they're not super interested in doing additional computation, but that's also now why we've become a bit more interested in exploring like how agents can plug on top of intense infrastructure. So for us, the lens that we view different intent systems through and how we actually evaluate intents in the crypto market is we look at three core components. Expression, so how much expressibility do users have when expressing their intents? Execution, what mode of operation do these solvers have? There's cows, obviously. There's RFQs, where basically solvers are filling orders directly. There's also just straight up routing. On Solana, you only have Jupyter doing routing, but obviously on Ethereum, you have a couple players. And then settlement. And settlement can take the form of just like a transaction on chain, or it could be processed, cross-chain, so you get some sort of proof that a bridging transaction actually worked or a cross-chain message was actually sent. So I then basically looked through and tried to understand everything I could about every intent protocol out there. There's a couple new ones that are out since I made this presentation, so it may not be fully complete. But yeah, so I started sort of, obviously these are the three major ones. So the main lenses with which I was assessing them is like, what can you actually do with these things? How is settlement executed? How is execution occurring? And how is expression occurring? And then for us, because we're very interested in the future where people can just say, hey, I want to do a swap and then be able to do things cross-chain, we also were trying to assess to what extent do these protocols do things cross-chain as well. And for us specifically, we're very interested in Solana, and also there's currently no Solana sort of intense protocol out there either, so that was also just a finding that we had. So you can sort of see there's a lot of similarities here, CowSwap obviously being different in terms of doing cows, 1-inch fusion and Uniswap X, you know, pretty straight up standard auction models with solvers that are just filling orders directly. They're both not permissionless, so there's no real way for, these are obviously things that are planned for the roadmap, but there's no real way for just some guy in some house to, in their basement, to just get set up and become a solver. Although there are now some conversations happening as well about enabling solvers with flash loans, so that could become a reality. Then we also have kind of the more cross-chain-ish intense protocols, across obviously being the notable one here, primarily focused on Ethereum and EVM L2s. How it actually works is the solver fills your order instantaneously, and then the solver is waiting to essentially a cross-chain message is sent from one chain to the next. Once that cross-chain is received on the other side, the funds are unlocked to the solver. There's obviously, you know, great benefits to that model whereby it's like really cheap and fast for the user, but for enabling a world where you have thousands of solvers doing this, it's a bit tricky to have your funds actually locked up for a period of time until a cross-chain message is sent. Then you also have Turn and Aori. Aori is an order book that is intent-based. They're currently live on Arbitrum and Base, but not doing cross-chain functionalities yet. You also have Turn, which is looking to modularize intents in a cross-chain method by essentially having executors that are performing off-chain logic. So they're also currently in testnet. Then you have us, Mantis. We are essentially a cross-chain intense protocol between, you know, on Ethereum, on Solana, and between Ethereum and Solana. So essentially on Solana, you could make a swap single chain as well, and that would go through our solver network and be filled by solvers. Jupiter's rolled out something called Jupiter RFQ, which is a bit similar. We use IBC protocol to send the cross-chain message. So essentially, a user that wants to swap from USDT to GOAT or whatever meme coin on Solana, the solver would fill their order directly, wait for an IBC message to be sent to the originating chain, and then the user funds are unlocked. So that's live. So we're live currently on Solana, Ethereum, and cross-chain, looking to add more chains in the future. So, you know, we are trying to craft the narrative and lead the conversation regarding intents on Solana, where I do think most people that are using agents probably will live. Then you also have another sort of cross-chain focused protocol called Near. They just rolled out their intents protocol, which apparently sits on top of their stack of everything else they're doing with chain signatures and other things. Their mission is to also extend this to Bitcoin and a couple other chains. So obviously their scope is a bit broader than ours, where we're very focused on Ethereum and Solana strictly at the moment. Then you kind of have a different flavor, which is people who view intents as constructing sort of each intent is a mini sort of machine as part of a broader execution location. So you have Anoma, which is building this intent machine, which to me feels as though they're creating a new VM for how transactions will be specified, and then solvers will have to come up with ways to compute those things and execute them. Essential is also doing something similar. I don't really have so much information about these two protocols, but my guess is they're trying to take intents in a different flavor as opposed to the existing protocols out there that have just traditionally been focused strictly on swaps. And then you have Enso and Kalani, both focused, Kalani more so than Enso, very focused on trying to expand the actual solver base. So trying to create a world where somebody in their mom's basement can basically run a solver. And to me, that's particularly interesting because you want to have as democratized of a solver landscape as possible. So in summary, I think 1 year ago, everybody was like, what are intents? What's happening with intents? Are intents just limit orders? I think the short answer is we know a lot more now about what intents are, which are specifying and expressing things to a system, executing those requested components, and then settling them. And now with the emergence of cross-chain intents, I think there's going to be a lot more definitions around this and what fairness actually means within the intent landscape. So based on all of this work done by other projects, we have been really trying to refine our vision for intents and the different ways we have solvers interacting with the system as well. So how we view them is we're starting with swaps, but we do want to move to a generalized framework to ultimately serve as an execution engine for agents. So I mentioned before, we are processing swaps on Solana, Ethereum, and cross-chain. We're currently in an effort to try to have this auction be as democratized as possible. We actually run the auction inside of the mempool of our Solana network extension. So essentially, we receive all these orders. The network extension is just used strictly just as a location for running the auction. Solvers directly tap into that mempool, come up with solutions, and then execute on these different locations. And the IBC framework, which we've deployed on Ethereum and Solana, is used to pass messages back and forth for settlement. So the first thing that we tried to understand when we were designing this was how can we, provide better execution given that there are multiple different ways of doing swaps. You can route through an AMM, you can fill the orders directly, and you can come up with cows. So we've obviously seen the work that CowSwap has done, and we were interested to see, to what extent, if you blend all these different types of filling orders together, what actually comes out. And so in this paper, we did exactly that and tried to study what are the effects of, solvers running these multiple different types of solutions for a single batch, and then extended this in the next paper, where we actually built these solvers in production and deployed them on Ethereum, and found that when you combine all these different types of orders together, we actually do get better placement of orders, and not only that, everything is much cheaper for the user. So I'm not going to go through the math and everything, but the paper's right there if you want to check it out. And so this is the model we're now running in production. We don't have cows enabled yet. We don't have cows on Solana yet, but we do have the routing component and the filling the orders component and the auction, and all this is now happening in a single location across Ethereum, Solana, and cross-chain. So now to us, where do you go from here with having, swaps, and the next step is, well, more swap capabilities. So we're going to be looking to add, stop losses and essentially creating more locations where solvers can compute and do things that will be helpful to the user. Now, the question is, like, will solvers actually do these things because they're historically very used to just doing swaps? That obviously does remain to be seen, but we believe that potentially introducing an additional sort of executor function on top of the solver could potentially be that actor that is triggering, you take an intent of, I want to buy Solana if Trump becomes president or something. Then this basically goes from, take this if statement, compute it, and then give it to the solvers. If the solvers only care about just-in-time solving solutions, they're not going to want to do that higher order thinking. So we're kind of trying to test out what this would look like by working with some agent teams, for instance, Allura and some other teams that are building AI agents, Spectral as well, by trying to understand, can these things live on top of an intent engine? And so, we have an SDK. You're able to just send orders directly through the SDK in TypeScript and Rust. And really now the question is, to what extent can AI actually be useful in terms of submitting things? Can they become this executor role is really the question. And the challenge there is if the AI doesn't have the right information or is not, or is triggering an intent that is not actually real, then they basically just screwed the user, and who are you going to blame? The AI. So there needs some sort of verifiability as well in place. And that's kind of what we're working on to try to create some sort of verification for these executors if we believe that agents will sort of evolve into becoming these executors for solvers. So yeah, to me, I'm very excited about the intent space. I think after 1 year listening to the presentations last year and coming back this year, I think there's been quite a lot of evolution in the intents landscape. I think all the talk that I've been seeing about agents is most likely going to morph the intent space into something that becomes a bit more robust, where we need some sort of executor function in place. And so, yeah, we're currently trying to understand what are the ramifications of that. Are we, we're doing research with Matias Ferreira at UVA about different auction models for trying to capture cross-domain MEV associated with agents operating on different chains. So yeah, we're very much so in the middle of still discussing these topics, but the good news is we're heading in some direction as an industry, and so yeah, happy to just take any questions.
Any questions for Omar? We have a couple minutes. I mean, I'm happy to ask a leading question. So you opened up, with this big vision of having talking to your phone, having AI agents place these intents. I guess what are the key unlocks that we need to get there? I guess presumably one might be that we have a proof that the translation from voice to intent is correct with a snark. You also mentioned the verification of the AI work with something else. Can you expand on that?
Yeah. So I believe the settlement problem has been mostly solved. For cross-chain, we have IBC now between chains. I believe the execution question is hard and being worked on by a lot of really smart people. And then the expression question is still the challenging one, right? So there are teams that simply just focus on how do I take the text that the user gives me and turn that into something that a blockchain can understand. And so for me, it's about the steps between expression and execution that need to be figured out. What that looks like is somebody needs to be able to take this information down to ways that, like if-then statements, simple statements, and then from there we need a way to actually trigger those if-then statements in a verifiable and decentralized way, not having some sort of central database that's just triggering things, because again, you could just blame the company that runs that central database for that, and then you need proof that that was actually real and done. And so I think probably some sort of marketplace could emerge where you have agents, you have this middle layer that's basically receiving all the information that the agents are propagating and processing, and then computing the outputs and trying to understand, did they do their jobs? So maybe it's sort of some sort of proof market that emerges for agents, but I think that's probably the requirement before you have the whole talking to your phone thing. Obviously, you can just replace the proof market with a central database, you know, just to test it out. But I think truly that's what we probably need for like real decentralization.
Got it. Thank you.
Thank you, guys.
Thank you so much.
Thank you.
Next up, we have Sam Hart from TimeWave, who will be talking on succinct program virtualization. Thank you. Thank you, Sam.
Hello. Can you hear me? So I changed the title of the talk. This is a little bit more, same general idea, but this is a little bit more direct with regard to what we're actually trying to do. So this is actually the first time I've spoken about any of this work. We've been building this for about 1.5 years, so it's an exciting moment for me to actually share some of it. So just to preface this, there's a conversation kind of emerging in the Ethereum space and I think elsewhere about just kind of re-emphasizing interoperability, which is really nice. I've been working for several years now in a kind of natively interoperable environment, and just trying to kind of glue together all the pieces that are required to actually make it work for users. So I feel like I have a little bit of a look ahead on some of what's coming. When you speak to applications, they just want to go wherever users and liquidity are. And you may not know what chain or ecosystem or technology you're going to be using down the line. So there's a lot of kind of new interest in deploying applications on Solana or deploying applications in new L2 that has a different virtual machine. It's very hard for Adapt to kind of pivot and support that new environment. So there are kind of new ecosystem actors that emerge that are domain specific. So we're kind of asking the question, you know, what if you don't have to make that choice? You don't have to commit to an ecosystem. And we're kind of contributing to this overarching goal of chain abstraction, ecosystem abstraction, really. Interesting. Ecosystem abstraction. So yeah, right now, if you're writing an application, you have a very kind of sheltered life. You get to have synchronous state, uniform execution model, and this is all going away when you start to deploy into another ecosystem. So high-level takeaways from this talk. I'll go into these more later, but sorry, something keeps flashing. It says use handheld mic on the phone. So just go closer, is that what's going on? So yeah, 99% of interoperability is just agreeing on the message format and getting your communication structure right. I'm going to kind of introduce a new way of thinking about smart contract execution that is more native to this interoperable environment. So overview of the talk, I could talk a little bit about some motivating examples and go into some of the product requirements that came out of that, do an overview of the system, and then get into kind of two aspects of the system. One is like integration with underlying domains and how to actually write smart contracts in a distributed setting. So first one, I picked this because it's kind of a popular example that folks might be aware of in this audience. So MakerDAO, now Sky, is trying to go to market on third-party chains. So L2s, Solana, eventually Sui, Aptos, things like that. They're deploying USDS, formerly DAI, into lending protocols on these chains, and they want to rebalance the capital that they're deploying there in order to equilibrate interest rates. And they're kind of outsourcing this function to Spark, as well as one or two other players. And Spark had to build an entirely new protocol to just to perform this function. And we went through a similar kind of experience, so their pain is like familiar to us. But the solution that they've come up with is very specific to one route, and there's just an enormous integration cost in order to deploy into EVM L2s. This problem is just super hard, so you need to accommodate lending protocols updating over time or adding new lending protocols. The actual strategy that you're using to rebalance might change over time. You may want to outsource aspects of it to someone like Spark. You may want to automate aspects of it, so that needs to be kind of swappable, and actually there's a lot of complexity kind of contained in the lending strategy. And then you need to be able to handle these catastrophic scenarios where just something blows up, like either the chain or the lending market or the counterparty collateral. This is an analogous example that actually prompted us to build this thing in the first place. So I've been working in Cosmos for a long time. As everybody knows, there's no liquidity in Cosmos, so we're just kind of beg, borrowing, and stealing whatever we could. And we think that this is going to be, we were kind of validated by seeing this whole thing with MakerDAO and Spark. This is kind of where I think we're going with protocol interoperability. So there's two places that you can get liquidity in Cosmos that are kind of untapped. One is liquid staking, and there's efforts to kind of increase the amount of free capital there. And the other is treasuries. And basically, we wanted to deploy treasury capital into DEXs in order to increase the liquidity so people could actually have good trade execution. So what we're doing here is we have, in Cosmos, every chain is a DAO, so it has the ability to execute arbitrary messages. So we have two chains, chain A, chain B. They want to pair liquidity and put that into a lending market. In this example, we have them transforming their native token into the liquid staked version of that token, and then putting it into a lending market, or in a DEX market, rather. Again, the thing about Cosmos, everything is an app chain, so this actually happens on 4 different chains. And none of these chains have, or not all these chains have virtual machines. They're kind of application-specific state machines. So this is really, really hard. It took us 6 months to build this application, just like specific to this use case. It's like building a rocket ship. Like you have to test this thing, and it has to work perfectly the first time. There's just like a one-shot, no room for margin. And in order to do this, we have a very advanced test suite that spins up all chains with multiple validators, deploys all the smart contracts required for the DeFi protocols that you're interacting with, creates IBC connections, runs relayers, then it deploys the contracts for the program that we built and simulates an execution of that program. So we actually spend most of our time just on like testing. After we did that, we kind of took a hard look and tried to understand, like, okay, if we were actually gonna have an environment in which we could write these things easily, what would that look like? So here's some of the kind of product requirements that one might want. The parties that are interacting with the system ideally aren't trusting you or your infrastructure. So you want the safety assumptions to be just dependent on the domains that are interacting with with your system. Liveness should ideally be anyone can advance the system. And then if you're going after this chain abstracted model, you need to abstract over a lot of different things. So what is the security model? What is the VM? What is the authenticated data structure? What is the serialization format, signatures? What's the token standard that you're using? State representation, fee models. I gave a whole presentation last year about abstracting over fee models and all the complexity that entails. Not going to talk about that this time. For ourselves, we want to integrate with an ecosystem once and not have to write it again. So we want a minimal footprint for integrating and something we can just kind of rely on and build, like layer additional functionality on top of. And then one of the reasons that this isn't available today or we can't take anything off the shelf is like this is all async execution. So there just isn't a model for how to do this. And then the types of programs that we're writing, we want to statically compile. We want them to, we want to know that they're safe on deployment, but we also need to have some runtime parameters that we're including in order to have accommodate for state changes that may be made as the program unfolds. Autonomous retries, failure handling, and then, as I mentioned, you want like super robust testing to know that you're deploying something that's going to work the first time. So just going to give a little overview of the system that we've made here. This is not like a complete system. Like I said, we almost like accidentally built this in order to serve our use case, and then just realized it's useful. So we're kind of building from the ground up, and that's going to be kind of the sequence that this talk that follows this talk. We talk about kind of the low level, and then when we get to the kind of high level expression and programming language design, we're still very much in early stages there. So yeah, our construction here is a program acts as a kind of control plane that is deployed as a set of ZK coprocessors that specific to each domain. So here I've depicted, 2 domains, 2 chains, like domain A, domain B, 2 coprocessors. Each coprocessor is kind of application specific. It has a precise fragment of that program behavior that's encoded. And like all coprocessors, they're executed as a pure function. And then the behavior of these coprocessors together composes as a holistic program. there is a connection between the coprocessor and domain that's kind of standardized, and we put a lot of work into just making sure that that channel of communication is makes sense for different domains. And once you've established this communication channel, you can query state, you can execute actions, you can commit to program updates. So here I'm showing like a program that bridges tokens from domain A to domain B. So we've essentially built this cross-chain execution environment that lives in the kind of in virtual space on the coprocessor across multiple coprocessors basically. So the programming environment that, you know, when you're writing the application, you compile that application to a set of build artifacts that are commitments to a ZK coprocessor or multiple ZK coprocessors on multiple chains. We use a resource model similar to Move or Anoma, and we're in kind of close collaboration with the Anoma folks. They have like really nice abstractions that we've borrowed from. And yeah, the resources, for those unfamiliar, represent ownership or execution rights within the program. They're UTXO-like, so one-time use. And then basically execution unfolds as the kind of consumption of resources that in order to advance program functions, and then the creation of new resources after those functions have been executed. So I'm going to talk a little bit about integrating into a new domain, like you want to integrate into Solana for the first time, or there's a new VM you want to add. So the first thing you do is kind of construct this connection. It is the single integration point with this domain. It tries to abstract over all the domain-specific details and give you a nice, like, uniform representation of that you can compute on. And yeah, it's built on authenticated message passing. These messages are conditioned on valid ZK proofs of execution. So that's the connection between the coprocessor, or like the message passing, and the valid advancing of program state. When you're inputting into the program, you're basically like, a user wants to move tokens into the program for the first time, or a DAO wants to move tokens to the program for the first time. You just transfer tokens into an account that's been initialized, that's held by this connection, along with any input state you might have. And then that you specify a register in the program that then constructs the associated resources and initializes that state in the program. When you've executed the program and now you need to move, like the program wants to move tokens out, that same connection can then perform a transfer and write to state or execute on a contract as needed. So I was talking to one or two people about this yesterday. We have this kind of hard problem of serialization. It's extremely boring, but I'll try to just go through it fast. Basically, you just need to represent the types of data on the other side. And so we have to have this kind of reference library of types. And we want to there's kind of an organizational challenge of making it so that you are doing this in a secure way with minimal amount of upkeep. And there are occasionally new built-ins that are added to VMs, so you need to kind of track all these things and make sure that it's all working. And so the test suite that we have helps with that as well. once you have this, this kind of type library, those can be imported into your program, and you can kind of wrap those and make them usable for whatever context you're trying to do. We have a relay infrastructure that tracks remote chain state and makes it available for execution. And then out of all of this, you get something like a getter and setter. And effectively, the ZK coprocessor has the ability to do anything that an EOA would do. So it can operate on behalf of, it can perform any kind of function, interact with any contract, move tokens, hold tokens, that kind of thing. We have this kind of library construction largely for convenience. Allows you to integrate with the kind of last mile smart contract infrastructure. So you have kind of the Solana types or the SVM types available to you. You have the encoding of the ABI, but now you need to know what the interface of SolLend looks like and represent that as like an intelligible abstraction. So you can bundle that as a library, and libraries are importable into your program. You can share libraries, so hopefully somebody only has to do that once. And eventually we'd love to land on abstractions for like lending protocols in general, or DEX protocols, or bank sends, that kind of thing. And this actually came up in one of the interoperability forum discussions I was in Bangkok. This is a general problem of interoperability that I think people are starting to come to. There's a lot of bespoke interfaces, and if you're going to write something like a DEX aggregator, it's actually an enormous amount of work to add any new protocol. So we would love something like that as well. So yeah, going to talk a little bit about what writing a distributed program looks like now. This is a radar image of a butterfly swarm, just as evocative what a program might look like. So our resource model, each coprocessor has its own memory layout that governs its execution. And these memory registers hold resources, which are, and the registers have conditioned access that encodes who can execute what, when. And I mentioned this before, but like resources are consumed at each step by functions, and new resources are emitted. At the end of the day, we get something that looks like that. We kind of visualize all the applications that we build with something like this. And it's effectively a Petri net. So we can kind of auto-generate like a unique Petri net for each program. These are some of the primitives that we kind of make available in the programming environment. We don't have like a fully fledged programming language right now, but these are kind of the early stages. So we have functions. Already kind of mentioned what they do. We have libraries that allow you to package a set of functions and perform this kind of mapping with the domain. Delegation we get for free out of the resource model. We can have kind of arbitrarily complex delegation to third parties just by adding an authentication method as the condition for executing the resource or consuming it. We have this notion of a subroutine, which provides a shared context for executing functions. And from those subroutines, you can define, that shared context can define partial orders of execution and atomicity of execution. Synchronous atomicity is obviously like straightforward, and we can do async atomicity through something like a promise. Right now, we have to do this kind of manually, but we want to build we want to do it a couple times and kind of figure out the right abstraction that we're going to build that and make it available for developers. Yeah, you can also compose programs relatively easily because they're all stateless. And they all have very well-defined inputs. So if you want to migrate a program or compose it with a secondary program, we can do that. Today, what programming looks like, you're either in one of two modes. You're either writing just like a YAML file, which is like extremely constrained mode of program definition that only allows you to do specific things, or you're doing like manual memory allocation. You're like the highest level or the lowest level possible. And we're building up to having a useful programming environment. We're kind of doing some research and looking at different models that we want to incorporate into our system. We don't really want to reinvent the wheel. So Move's object model is really nice, and the kind of the developer approach that they've taken. We're also looking at like Erlang's supervisor trees. We have a similar kind of restart system or like queuing system that is incorporated into the coprocessor already. Other than that, it should just feel like vanilla Rust. So we recently had a little like internal hackathon thing. What took 6 months to write, that multi-domain liquidity sharing agreement, now takes 2 days. So really nice. It takes 2 days if you already have the test environment set up. That's actually one of the most difficult things. So we're putting a lot of effort into trying to make it as easy as possible to kind of instantiate these test environments. It's very, very challenging because they're extremely heterogeneous. And then, yeah, some of the things that one could write with this are, if you want to do a cross-chain protocol guild type thing, you could do periodic payouts and like swaps in the middle of a payout if like a user wanted USDC instead of ETH or whatever. You could do a dominant assurance contract with like multiple chains, cross-chain vaults with complex yield strategies. This is not an intent system, but we think it's like very complementary to intent systems, and basically the delegation model or these resources allow you to kind of overlay intent systems where needed. I guess I've learned through experience that like an intent system means nothing if you don't have the ability to execute the transaction manually at the end of the day. So you kind of need both of these things available. And most intent systems need liquidity, and so it's going to be very hard to serve an L3 with an intent system. So there's going to need to be some manual execution going on here. So summary. Yeah, we put a ton of effort into implementing this connection abstraction, just kind of cleanly separating the domain details so that when you're writing the program, you don't have to deal with that. We have a lot of kind of secondhand benefits from having this resource model and using pure functions. We can build up abstractions very easily now. Yeah, I guess just to conclude, I want to impart a little bit of this programming paradigm that we're trying to introduce here, which is these programs are not centrally controlled. Like there is no center to them. You are defining the program and then kind of setting it free. You're integrating it into the site of local execution. And I think this is like a really beautiful model of computation that actually works quite well with the type of challenges that we're trying to solve here. It is a very decentralized model of computation. So yeah, we basically provide a common language of interaction between these fragments of execution. We structure the expected communication in advance, so we statically deploy the program. And then the general approach here is to enable intelligent local execution, which, in aggregate composes into this kind of program whole. So yeah, a little bit of a new take on what an interoperability story might look like for cross-ecosystem or cross-domain interactions. Thanks.
Thank you, Sam. We have a couple of minutes for questions. I guess one question I have is, I guess you introduced ZK as a new ingredient in the design. Like, what is the unique unlock that you get from ZK? Yeah,
the talk was originally all formulated around that question. I was like, I should just explain what we're doing. So right now we're actually not using ZK, but I frame the talk as if we're this is where we want to go, and we have we're doing kind of tests as the tests with RISC-0 and Succinct in order to get there. ZK is really nice for a couple of reasons, and maybe one thing for this audience is so there's a couple nice things. One, there's a kind of race to the bottom with RISC-V in particular. So we can expect the proving time, the cost to actually perform the execution, the proof size, all these things to go down over time. And from what I've heard, there's orders of magnitude compression that we can get just based on known techniques. So that's really exciting to just be okay, I can do my part, and then over time, my business just gets better without doing anything. The other thing that it offers is the smallest possible integration footprint. So went through this with attempting to integrate IBC into different domains, which has been done, but there is a lot of machinery in the IBC protocol that handles connection handshakes and has to track specific state and do deserialization, all that stuff. And you can throw almost all of it just into a ZK coprocessor. It's going to take, you take a performance hit, and you now have to do this in an asynchronous manner, but you can write that once and then deploy it anywhere, which is super nice. So there's going to be, or there already is a RISC-V ZK prover for Solana. There's, of course, several for EVM. There's one for CosmWasm or WASM-based machines. So yeah, the techniques that I kind of described here, you just have to worry about this kind of serialization problem and the message passing problem, and then you target, after that, you can target a well-defined data type and just operate on that.
Hey, so we'll see if this question makes sense. But I want to use myself sort of as almost a guinea pig, because I feel like it's super interesting what you're talking about here, but that I'm somehow missing some essential component of what you're selling me. So
Yeah.
I mean, not that you're selling anything, right? But let's say I'm some application developer building an application across a couple of domains, relatively heterogeneous.
Mm-hmm.
yeah, what is this new thing that you're offering? What are the new tools that you're offering me in practice? I guess it's like a different type of environment to orchestrate these, or like a paradigm for how. This is where I wasn't, exactly sure.
No,
So-
I mean, like I said, this is the first time I'm really explaining it, so I'm not good at this yet, so I appreciate this question. So how do I write smart contracts today? Like if I'm trying to write a Solidity contract, okay, I like pull it up in my code editor, I have a way of simulating execution, I deploy it to a domain, like that's great. How do I do that if I just want to do it like on base and mainnet? Well, I actually have two programs. Like now I have two things. Like there's no like shared environment here. So even when you're not even considering like cross ecosystem, there's a lot of pain. And so like one, we solve that problem. There's a single environment that you are in, you write the program there. It is an asynchronous program, but like there's a single world that you're in. And then we create this kind of hard boundary between the underlying domain and this kind of virtualized, it's a virtual machine. That means that you have all the same abstractions when you're working in that environment. So I just want to interact with the lending protocol. I have the types of that lending protocol that I've kind of like predefined in my native types. And so if I want to go from lending protocol, from Aave on Base to Sollend on Solana, those are just like, they're the same kind of object in my world, and I just pass a message from one to the other.
So I can deploy things on this new venue, so these programs or these smart contracts that now can, I can work over these abstractions on the multiple venues, and this is what I can use this system to do that.
Yeah, one of the things is not a lot of people have worked at this level before, so it's going to be unfamiliar to a lot of people, and this is why I brought up the Maker example, just because it's like early example of somebody trying to do this. We are going here, though. This is necessarily what's going to happen. You're going to try to unify liquidity. You're going to try to like reach users elsewhere. And as soon as you make that step into like multi-domain or multi-execution environment, it is just an absolute nightmare. And you need something like this.
Talk, Sam, thank you. Question about the functional programming. Was that something that started really early on as part of the like initial vision, or was that something that emerged kind of out of necessity in the middle or end of the project?
Functional programming?
Like the use of all the functions to not hold state.
Well, typically that's how a coprocessor is designed, but there is a justification. So I've tried to avoid this analogy to some extent, but I think it's helpful. It can be helpful or confusing, so sorry in advance. To some extent, what we're trying to do is play the role of a user, like a normal user. And if you're a normal user, you can go to Ethereum and you can like execute a transaction on Uniswap, and then you can move those tokens onto Solana via Wormhole, and then you can like trade over there and whatever. Like you have the capacity to like move between different programs, and your client builds transactions for you in order to, or helps you build transactions, then you choose to execute them. So we're like kind of playing, we're like a trustless layer that does that thing. And each of those interactions is kind of a pure function in a way. Like you build the transaction, and then once you execute it, that's it. Like all the information that you need is contained on the chain. And so we just use the same model because it actually matches the interaction pattern that we're trying to model here.
Amazing. Thank you so much, Sam. Our final presentation in the interrupt session is from Sarah Azuvi, who will be talking about secure cross-rollup communication.
Is this working? Yes?
Yes.
Okay. Okay. Hello, everyone. Hey, thank you so much for staying till the last talk of this session. The work that I'm going to present today was done jointly with all my amazing colleagues at Scroll. So Alejandro, Mohammed, Jonas, Peter, and Dom. So during this talk, I'm going to start by giving a bit of background about what is interop and why we need it. Then I will go over the technical challenges that we face when we design an interop system. I will go over the different components and different architectures that we can have. And finally, I will present our own design, the Scroll Interop Gadgets, or SIG for short. Okay, let's start with the background. So we all know that since 2020, Ethereum has moved to this roll-up-centric roadmap. So yeah, the aim of this was to have better scalability and cheaper prices. And well, it's been going very well. Now we have a lot of L2s that are out there on Ethereum. Like they have very big TVL, they're offering good price, good scalability. Some of these L2s even have now their own network of chains, so even more roll-up, even more chain. So that's great. But also there's an obvious problem with this, and that's fragmentation. So what is interoperability? Interoperability is the ability to move assets and data on two separate chains. So for example, let's say I have my accounts, my wallets on one chain, Scroll. I want to buy my coffee, but the coffee shop is on Arbitrum. So the Strawman approach to solve this problem is to have two transactions, basically one transaction where I'm unbridging my coins from Scroll to Ethereum, and another one where the coins goes from Ethereum to Arbitrum. But then that's annoying because that's two L1 transactions, it's slow, it's expensive, it completely defeats the purpose of L2. So when we think about interop, what we want to think about is, can we instead have like the transaction going straight from Scroll to Arbitrum and not go through the L1? So that's what we want to do. And hopefully have something much faster and much cheaper. Okay, so why do we want this? I think that's pretty obvious because this is a big UX pain point. Obviously, you know, if I have my wallet on Scroll and I don't want to go through the L1, like now I don't know, do I need to have a wallet on every rollup? Basically that's just annoying. Like liquidity is dispersed across all chain. Also for DeFi application, it's quite inefficient. Also, this really weakens smart contract composability. That's one of the big features of Ethereum. We want to have the ability for smart contracts to be composable, to interact with each other. If they are in different chains, that's much harder. And lastly, having interop helps lower the barrier to entry for new L2. So basically, if you're a new L2 and you want to come into the game and you want builders, developers to build on your platform, if they can have a way to tap into the liquidity of, for example, Arbitrum, then it's going to be much easier for you to break this network effects. So basically, this creates healthy competition between the L2s, which is really good, and more decentralization and better environment for everyone. Okay, so hopefully we are all convinced why we want to do interop. So what are the technical challenges associated with doing this? So first, again, kind of repeating myself, but what we want to achieve is low latency, cheap transactions. So as I said, we don't want to have to go through the L1 because it's slow and it's expensive. And obviously, we want security. We don't want to trade off security. So we have identified three main problems that we think are the main problems we're doing this type of system. So I'm going to illustrate them right now. So the first one is invalid state transitions. So imagine we are in this situation, we have to roll up two chains, and there is one transaction on block B on rollup B that depends on the states of block A on rollup A. Then what happens if block A is invalid? So for example, again, if I'm buying my coffee, what happened if in block A, my transaction where I send the money for my coffee is in a block that is not valid anymore. Then block B depends on something that is not valid, so we have big inconsistencies issues. So basically what this means is that in this concept, rollup B has to verify the state of rollup A, otherwise we have issues. And also this can create some quite complex dependency graphs. So what if rollup B verifies the state of rollup A, but then rollup A also depends on another rollup who depends on another rollup. So lots of complexity can arise here. Although this kind of thing can be solved with real-time proving. So if we have, for example, real-time, like ZK real-time proving, or even using trusted hardware, TEEs, that's something that we could potentially solve. And hopefully we'll have real-time proving for ZK pretty soon. We're making great progress on this aspect. Now, another problem that cannot be solved just using ZK proof or TEEs is equivocation. So in that case, what if block A was perfectly valid, and you have a proof of this, but there is an equivocation, so there is a reorg. There is another block A prime, and A prime is the block that is part of the final state. So again, to go back to my coffee example, in block A, I'm sending the coins to the coffee shop, but in block A prime, I'm sending my coin to buy some food. So basically, this is a successful double spend. Obviously, that's super problematic. So we also want to account for this. And last issue I want to talk about is like now, what if block A is valid, there is no equivocation, everything is well, but for some reason, rollup A just goes offline and does not settle its states on the L1. So basically, there is my transaction, buying my coffee, but it never makes it to the L1. So it's never settled. So then block B is still in a bad position because it depends on the state that is never finalized. So basically, to solve this issue, you will need to have some kind of data availability solution. So just want to emphasize here, so these are the main three problems. Oops, there's something a bit wrong with my slide. I wanted to emphasize the equivocation problem, not this. But yeah, what I was going to say is, like, as I said, like the first problem about invalid state transition and non-settlement, like they can be solved with real-time proving, with TEEs or DA solution. And I think equivocation is really the biggest one, biggest problem here that we cannot solve with this type of proof. So that's going to be our focus. Okay, so now let's go over what are the different components needed for an interop system. So first, obviously, if you want to roll up or to chains to interact with each other, you need a message system between these chains. And this is something that the previous speaker obviously highlighted also in his talk. So that's done. Then in terms of security, I have mentioned three problems. So basically, what we need is a solution to this three problem. We need to have a way to verify state transition. We need to have a way to prevent equivocation and to enforce liveness. So again, these are the three problems that I have just described. We need a mechanism to solve them. And lastly, we also have a settlement layer. So as we know, L2s, they need to settle to the L1. They need to interact with the L1. So they need to have a roll-up contract where they can push their steps. So for example, for ZK rollup, they will put their ZK proof. And also a bridge contract on the L1. This is to bridge like your coins from the L1 to the L2. And in the case of an interop system, potentially, these two contracts that are on the L1, they could be shared between multiple rollups because we want to have interoperability. So you could think that you could have one bridge contract for multiple rollup. And lastly, we also need to have an economic layer. So basically, we want to make sure that all of the actors are incentivized to behave well. Okay, now I'm going to talk about different types of architectures that we can have for this type of systems. First one is what we call the mesh model. So in a mesh model, rollup communicates directly with each other. So basically what this usually means is that they have to trust each other. So this can create, I've already mentioned this, quite complex trust dependency graph because trust is transitive. So this works well if you have a small set of big trusted rollups. So for example, if you think about Arbitrum and Optimism and Scroll, like they could, have some trust into each other. But then what happens if there's another smaller L2 that comes? Maybe it doesn't have big TVL. You don't really have any reason to trust it. And then if one of the rollup trusts it, then by transitivity, everyone in that dependency set also has to trust it. So basically, we kind of like end up with some kind of cliques, like cliques of trust, and that's not great for smaller L2s. This is, by the way, the model that is used by Optimism, Superchain, and also Arbitrum Orbit. Now, another type of model that we can have if we don't want to have these trust cliques is the hub model. So in that case, we have a shared interop layer, and basically all the rollup use this interop layer as kind of like their single trust point. So they don't have to really trust each other as long as everyone interacts with this shared interop layer, then this enforces the trust. And this can also help for liquidity management. So for example, Polygon and Espresso system, they have this type of architecture where they have this shared layer. Another difference that I want to highlight in the design of interop system is in protocol versus out of protocol. So out of protocol, basically what this means is that no modification is needed at the protocol level. So basically this gives higher flexibility. So this is the case for liquidity bridge. If you think about Chainlink, CCIP, or Axelar, or Across, they are basically smart contracts that are built on the rollup. So basically, you can integrate them without making any change to the protocol specification of the rollup. So this is pretty good. Now, on the other hand, we also have in-protocol solutions. And this, as the name suggests, in that case, this requires some changes at the protocol level of rollup. So what this means is that there is limited interoperability. You cannot just interop with any other chain and create a smart contract on them. They have to agree to change their specification for you. So this is definitely less flexibility, but also you can gain more. Obviously, it's a trade-off. So for example, Superchain, Elasticchain, and Arbitrum Orbit, they are in-protocol solutions. So they can only interop within each other. Okay, so now that I've given all of this background and all of these design shows, I'm ready to introduce our own design that we did at Scroll, the Scroll Interop Gadget, or SIG. And I'm just going to give a quick disclaimer to say that all of this is work in progress. It's by no means meant to be a final design. And we would be really happy to have your feedback on this. So yeah, you'll see I'll mention it. Like a lot of decisions are temporary decisions in the design. So I'm going to start with a quick overview. So I already mentioned a shared bridge. So in our design, we have decided to have a shared bridge between all of the rollup within our network. And this is basically to reduce L1 cost. However, if you have a shared bridge, you're also losing a bit of sovereignty. I've just talked about in protocol versus out of protocol. So we are also looking into ways to have good guarantees without having a shared bridge. As I said, still work in progress, but in this first version, we have a shared bridge. So we have a centralized entity that we called the orderer. And this entity is going to be responsible for preventing equivocation from happening. So again, remember when I was talking about all the security issues, I said equivocation was the one that we are the most concerned about. So we have basically this entity that helps prevent this. Obviously, having a centralized entity is not something that we want on the long term. So this is the plan is to decentralize it. You could have a consensus protocol, a network, but that's for the future. So again, same before I was talking about how we need to verify the validity of other chains. So to do this right now, what we have is like we ask that each rollup runs a follower node of each other rollup that they interact with. So basically, as a rollup, you are responsible for verifying the states of the other rollups. So obviously, that's not scalable, and this is not something that we want to keep in our future design. And as I've already mentioned, we could replace this by using trusted hardware or ZK real-time proving. But this is a placeholder. One other thing is that we have a common proof system. So in this design, all of the rollup are the same. And because scroll, we are a ZK rollup, this means that every other rollup is a ZK rollup. So to reuse the terminology that I have introduced before, the SIG is a hub design. It's in protocol, so we ask that every rollup that wants to be part of this network has to follow our specifications. And it's homogeneous, meaning that every rollup for now uses the same proof system. Okay, now let's go into the more technical detail. So as a rollup, if you want to join our system, as I said, you need to join the shared bridge, and you do this by depositing some stake. And this stake is going to be used for slashing, so basically to incentivize you to behave well. Then what's going to happen is whenever you want to settle your state, first you're going to send your metadata to the orderer. The orderer is going to verify that you are not equivocating, and if everything goes well, it's going to sign your metadata. And then whenever you want to settle, you're going to send your metadata together with the signature from the orderer and a ZK proof because we are a ZK rollup. So essentially what we do here is that we just add a signature from the orderer to prevent equivocation. So it's like one additional step compared to the normal rollup interaction. Now, we also want to leave some sovereignty for the rollup. So we don't want to force this order attestation, and also maybe the order is offline, something happens. So we also want to give a way for rollup to settle their state without this order signature. So in order to do this, basically this is a two-step process. So first, as a rollup, you're going to send a pre-commitment to the shared bridge. Then you're going to have to wait for a small delay. And this small delay is going to give the chance to the orderer or to anyone else to potentially spot an equivocation. I'm going to give more detail about this in the next slide. Hold on. If everything goes well, after the delay, this pre-commitment becomes a commitment. And then you can just settle your state the usual way. Okay, so I've talked about equivocation a lot. So now let's see what happens if a rollup tries to equivocate to see how we handle it. So again, now we have a malicious rollup that wants to submit an equivocating state to the shared bridge. So by definition, because the orderer will never sign two equivocating states, this means that rollup A has to take the slow path that I've just described, so basically settling without the orderer signature. So rollup A will submit the pre-commitment to the share bridge. Then rollup A will have to wait for a delay. And basically, before the end of the delay, the orderer will be like, wait, this is an equivocation. I have signed another state, or like there is another state that exists. And obviously, that's very easy to prove. And basically, what this means is like this prevents the pre-commitment from being transformed into a commitment. And then rollup A is slashed. So effectively, basically, you just post a proof of equivocation to the rollup. Now I'm going to go over some quick economics consideration that we need to make when designing this type of system. So most of it is like open problems that we are currently working on. So yeah, we need to figure out the deposit and slashing associated with equivocation. There's also some slashing associated with liveness that I didn't get the time to discuss, but that's also some economic question. We need to incentivize the orderer. I haven't talked about message passing because, again, because of time, but if we think about relayers that helps send message across the rollup, then we also need to incentivize these relayers. And obviously, we need to talk about transaction fees because now, if you do a cross-chain transaction fees will need to pay potentially 2 different sequencers, maybe the orderer, maybe the relayers, so it's going to be more complex. So these are the things that we are currently investigating. Okay, so I'm going to finish by just giving a quick comparison with other systems. There are a lot of systems out there, projects out there that are doing interop, which is amazing. So I've mentioned Liquidity Bridge already, which are amazing because they are on the application level. They are out of protocol, so they are very easy to integrate with rollups. However, they need liquidity on both chains that they want to help interact. So that can be pretty expensive. And also, it works really well for liquid fungible assets, but less so for example, NFTs. I've already mentioned Optimism, Superchain, Mesh Design, super cool system. One thing that they have is that this property called cross-chain contingent blocks, where basically this means that if one block in the click reorgs, then every other blocks that depends on it has to reorg too. When we did our design, we wanted to prevent reorg. AgLayer is another super cool design. Again, I've mentioned it's a hub. So they use this pessimistic proof to verify chain validity. As far as I know the design has been changing a lot, but to the best of my knowledge, they do not prevent equivocation. Hopefully, this is still the case. And lastly, Espresso Systems is something that is super similar to our architecture that we think is a really cool project as well. Although they are slightly different, they are basically a marketplace for sequencing, whereas in our case, we don't really do shared sequencing, and we really design our system trying to have as much modularity in mind. So, for example, you could join the orderer or the share bridge, or like just the share bridge, but not the orderer. So we really like designing in a kind of like more minimalistic and modular way, but also a really cool and similar system. Just one word to say that this list is obviously non-exhaustive. There are, as I said, lots of projects out there. So sorry if I didn't mention your project. Sometimes it's even hard to keep up with everything that's happening in this space. But yeah, it's really cool that everyone is working on this because this is really important. Okay, so we are out of time, and I'm just going to say that we have a blog post that is going to describe what I've just presented today in more details. And it's going to be out, I think, next week or very soon, if not next week. I think next week. So keep an eye out for this. Also, if you're interested in all of these problems, feel free to contact me. And maybe, I don't know if we have time for a question. Otherwise, thank you for your time.
Thank you, Sarah. We do have a couple of minutes for questions. I guess one question I have is, can you talk more about the shared bridge and how do you solve the coordination problem to getting multiple parties to opt in?
Yeah, so basically, as I said, like the shared bridge is something that we decided to do because we want to reduce the cost of the L1. So indeed, this kind of like require the roll-up to lose a bit of their sovereignty because then they have to join our bridge. But then what this means is that they shared the custody of the asset on the same smart contracts. So it's really good because then if you have different bridge, then ultimately you will need to have more L1 transactions that send assets between the different bridges. If you have everything on a shared bridge, you don't need to do that. And what we have actually had one slide about this that I didn't put in the presentation because of time, but what we have is to help with the rebalancing and the accounting of assets. In the shared bridge, we use ZK proof. So basically, you would take a ZK proof of all the incoming transaction and outgoing transaction to verify that assets are well rebalanced.
In your scroll design, what happens if you have a liveness failure on the order, but there is a equivocation raised by rollup?
So yeah, I didn't also have time to go over the liveness issue, but basically what we are going to have is that if someone goes offline and didn't submit the state, what we want to do is like after some time allow anyone to just prove their settle their state for them. So basically anyone, like again, if we have real-time proving, then it's great because you have the ZK proof that is already computed, and then anyone can submit it to the L1. Even if that rollup goes offline, and even if you don't have real-time proving, if you use some DA solutions, then anyone could compute the ZK proof for the rollup that has gone offline and submit it to the L1. So that would be basically the mechanism. Thank you.
Okay, next up we have a break, 15-minute break, and then we'll have the macro session. Thanks again, Sarah.